Today's lesson is about L'Hopital's rule, a very cool way to find limits that used to be out of reach for us before. So here's an example. The limit of x squared plus 2x minus 3 over ln of x as x approaches 1. If we were to try direct substitution, we would find ourselves stuck. If we try to do it with direct substitution, we get 1 squared plus 2 times 1 minus 3, that's 0, over the ln of 1, which is also 0. And we know that 0 over 0 is what we call an indeterminate form. It means that we don't have an answer yet. It doesn't mean the answer is infinity. It doesn't mean the answer is 0. It doesn't mean the answer doesn't exist. It means we don't know it yet. Very, very early in the year, we learned some strategies for dealing with this. The number one strategy was to factor and cancel out. But you can't factor ln of x, so you're not going to get anywhere. So we're stuck. We learned about rationalizing the numerator, but that doesn't help us here. There's no way. The numerator is already rational, and it still doesn't help. Okay, so the other method, what we're going to learn today, is called L'Hopital's rule. It's not that hard to do, but the setup is very important. So I want you to pay close attention when I actually do the problem so you can see what we do. The property of L'Hopital's rule says that if you have some function that's a fraction of two other functions, f of x is g of x over h of x, and both the limit of h of x and the limit of g of x as x approaches some c is equal to 0. That's big. You have to show that that's true in order to do the rest of the rule because of this if here. Without that statement, the rest of the rule doesn't exist. But if it's true, then the limit of the fraction we're looking for as x approaches c is equal to the limit of not g of x over h of x, but g prime of x over h prime of x as x approaches c. So the limit of a quotient equals the limit of the quotient of the derivatives. If direct substitution leads to 0 over 0. And it's also true for infinity over infinity. So if we're going to try and take a limit, like the one we just tried before where we know we ended up with 0 over 0, but nothing factored, couldn't do anything, if we can show that the limit of the numerator and the limit of the denominator are both equal to 0, the limit of x squared plus 2x minus 3 as x approaches 1 is equal to 0. That's true. And the limit of the ln of x as x approaches 1 is equal to 0. That's also true. Make sure you say this as two separate statements. Don't do what I did on the last page, which is just say this equals over 0 over 0. Nothing can equal 0 over 0. 0 over 0 is undefined. So don't ever say equals 0 over 0. Make the statement as two different limits. Then you can say, okay, that means that the limit we're looking for, which I will always rewrite so that I'm making a full statement, the limit that we're looking for is equal to not the derivative over the derivative, but the limit of the derivative of the numerator over the derivative of the denominator as x approaches 1. That limit notation has to be there. But now I can do direct substitution, or at least I can try it. If I try direct substitution here, I get 2 plus 2 is 4 over 1 over 1, which is 4. And so that's my answer. We found the limit. If you want to verify it just for fun on Desmos, we can type in x squared plus 2x minus 3. If that happened. X squared plus 2x minus 3 over the ln of x. And we can see as x approaches 1, we can see the graph is getting closer and closer to 4. When x is exactly 1, we know that there's going to be a hole there. And that's why we couldn't just do direct substitution. But we can see that the limit does definitely appear to be 4 with the graph. So that at least backs up what we claimed. We'll look at another one here. Actually, I'll jump down to this one. We'll do this here. The limit of x squared e to the negative x as x approaches infinity. Now, your first thought might be, wait a minute, that's not a fraction. But remember, e to the negative x can certainly be written as over e to the x. So we can certainly turn this one into a fraction. and then verify. We tried direct substitution first, and I'm going to erase this in a second because it's not going to work, but infinity squared over e to the infinity, well, those are both infinitely big. They both grow without bound. So I need to say that in the correct way. The limit of x squared as x approaches infinity equal infinity makes me a little bit uncomfortable. If you say it, it's fine. Perhaps a better way to do it would be, say, approaches infinity. Put an arrow there. And the same is true for the denominator. The limit of e to the x as x approaches infinity also approaches infinity, which means we can use L'Hopital's rule. I don't need you to specifically say L'Hopital's rule because you're going to apply it. So we'll start with our original limit, which according to L'Hopital's rule must be equal to the limit of the derivative of the numerator divided by the derivative of the denominator, still as x approaches infinity. Which, we have a slight problem, is still going to be infinity over infinity if we try the direct substitution. So we'll have to apply L'Hopital's rule again and say the limit of 2x as x approaches infinity is also infinite, and the limit of e to the x as x approaches infinity is also infinite. So we'll have to do this again, and this is something that happens a bunch with L'Hopital's rule, that sometimes you got to do it again. So the limit of x approaches infinity, the limit as x approaches infinity of x squared over e to the x. I'm going to write both steps here. If you kind of skip this middle step, I will forgive you. But that has to be equal to the limit of the derivative of our second numerator divided by the derivative of our second denominator as x approaches infinity. And this time we can do the math. If you do direct substitution here, you get 2 over infinity, which approaches 0. So our limit that we were looking for must be equal to 0.